So I'm pleased to welcome James Pallister from the University of Bristol. James's actual expertise is in low power and power reduction, particularly looking at the software and compiler side as well as the hardware. And actually a lot of his work has been done using the XMOS processor, which is David May and XMOS's parallel version, often regarded as the child of the transputer. But he's going to talk today more generally about parallel programming and some of the general concepts behind parallel programming. Okay, James, over to you.
So, as Jeremy said, I mainly do a lot of energy efficiency work, but I've been working with the XMOS processor. We've got an old version of the Epiphany board here, which you can't see the numbers, but it's running dangerously past its nominal voltage, and it didn't blow up. But today I'm going to be talking about some other stuff. So, parallelism versus concurrency. A lot of this will be repetition now, but it will be good to drill it into you. We'll talk about the effect of communication, why parallel programs often break on these deadlock or race conditions. Then a bit more specific, we could talk about the Epiphany's interconnect and some unique challenges that arise from the determinism that's built into it. So again, why parallel? The world's parallel. I find it interesting that our brains are hugely parallel, yet we force them into writing sequential programs. We've all been taught to think sequentially from the processes that we've grown up with. The frequency scaling has meant we don't have to go parallel, we can just get a faster processor and our programs run faster. Nowadays we have to go parallel. And this will make it future-proof and it's generally a good thing. So let's just define it to begin with. What is parallelism? Parallelism is, in the simplest sense, doing more than one thing at the same time. So you can see we've got gophers here. We've got one gopher delivering books to burn them, and the parallel version of two gophers both delivering books to burn them. It's taken from Go's language, yet another parallel language. So it's interesting to note that parallelism versus concurrency. Concurrency is an innate property of the program, whereas parallelism is actually doing two things at the same time. So you can have concurrency without parallelism, but you can't have parallelism without concurrency. And how much faster you get from going parallel is worked out by this lovely diagram. So Amdahl's law in pictorial form, if we have our program split into two sections, one serial, one parallel, we can do, and this is, we've got 4 seconds of stuff which could go in parallel, and 1 second of, say, initialization. It's going to take 5 seconds overall on one processor. As we increase the amount of parallelism we've got, we see it gradually getting smaller and smaller, until we've got 2 seconds for 4-way. But it's not 4 times faster, it's only just over 2 times faster due to this serial part. And that's the best you can do in this case. So perfect scaling, the thing that we all aim for, this nice straight line up the middle, 50 cores, 50 times faster. Doesn't usually work, doesn't ever work. If 20% of your program is serial, the speed up drops off incredibly fast. So you hit 20 processors and adding more isn't going to make much difference at all.
And the overhead is doing all that, and it goes slower.
Yep, and the next slide. And it goes slower. So, as you can see, 20% again, peaks at about 10 cores. So this is with a particular communication overhead. You can change the communication overhead, and that will make it better or worse. this is just factoring in communication, so the real life version. I'll just let you look at that for a minute. These all show how cores interact with each other for different types of programs, different programs. We've got lots of different benchmarks. This was a study done last year, looking at different programs and how different cores communicate with other cores. So up on the side, we've got cores producing data, and along the bottom axis, there's cores which consume the data. And one thing that you immediately see is that they tend to communicate locally in many, many cases. So you often see it's communicating with adjacent processors or just one or two other processors mainly. There are other degenerate cases where, for example, this one here communicates with everything. But on the whole, that doesn't happen as much as you might think it would. So that might become a bit more relevant later when I start talking about different types of programs. So now on to different ways we can split up our data between our instruction streams. So historically, most of our computers have been single instruction, single data. So you take the latest Intel processor, it does have SIMD instructions, but what it would do is take one instruction, take one bit of data with it, and perform that instruction on that bit of data. We then get the extensions to this, which are fairly easy to implement from a processor point of view, but not necessarily that easy to use. We've got SIMD, so you have single instruction and multiple data. So these long vector types with different bits of data going in one instruction. This is also very similar to the way GPUs work. They'll take one instruction, distribute it through many different functional units, and then the data the pixels will filter through and be processed in this way. One thing that we don't usually see is multiple instruction, single data. So this there's very few examples of this. It's sometimes used in verification, so if you have to check that your results are correct, you'll have data, push it through different versions of the same algorithm and check that the results are the same. Another thing that is useful for is signal processing. So if you're processing the same signal but in different ways, and then combine them, you can do multiple instruction but single data. It's the one of the four that doesn't get used that much. And then we come on to multiple instruction, multiple data, what the Parallella is. The most flexible of them. Lots of different processing units. We have multiple instructions, we have multiple data, they communicate with each other, and it all gets a bit more complex. So the 7 dwarfs of parallel computation. This was mainly a HPC kind of view, so supercomputers. We've got stuff like the structured grid, where you use fluid simulations to do things. You've got the unstructured grid, which does similar things, but they're used in aerodynamics, wind tunnel simulations. Monte Carlo again, this is showing Monte Carlo integration. But Monte Carlo also gets used a lot in a verification of electronic circuits. We can test at different process corners, you can test different variations in transistors and check that it still works. There's other stuff like N-body, which particle interactions gets used a lot in very detailed simulations. And then there's other methods such as spectral and deep dense and linear algebras. So if we look back at this slide, almost all of these will fit into one of those categories. So next, I'm going to give you a quick overview of the different paradigms a few of the different paradigms that you often see in parallelism. So a very popular one, which I've mentioned already, pipelines. requires that you can actually decompose your task into lots of separate stages which you can then distribute over many different cores, and it will incrementally operate on the data and build up the task that you're trying to do, and you eventually get your car made at the end. So this, if you can decompose your algorithm in that way, you manage to get a speed up just because you can overlay different portions of the operation at the same time. So instead of doing the entire thing, then doing the next block, then doing the next block, you can parallelize them, put them in a pipeline. And this is very similar to what we've seen our processors in hardware. We see different stages of instruction going through the instruction pipeline and being executed in parallel. Task farms, this is seen a lot. The client-server model, you have one centralized entity which will then distribute work to many others, and then they will go away, process this work, come back, ask for some more. And while this sounds like a good idea, and sometimes it is, but the communication overhead. You see all of these workers are communicating with the same farmer. And quickly, if that farmer can't respond fast enough, it will get over. The communication overhead makes it unmanageable. And you get this catastrophic slowdown. And the last type that I'm going to talk about, geometric parallelism. So this is based on the layout of the data. So sometimes physical simulation, sometimes other things like matrix multiply. You can see on the right here, we've got the matrix multiply is essentially laid out in that way, so you can take the columns, you can take the rows, you can parallelize it in that way to get more parallelism. And I think Simon's going to be talking to you later about an exact example on the Epiphany, which will run this way. And then there's simulations. So this was parallelized in each cell in this, each pixel essentially is running on a different processor, and the whole thing runs in parallel. So an example of how you can decompose tasks in this way. This is a MPEG decoder, and at each stage there you get a different kind of parallelism. So you can see that there's these two tasks here which can be done in parallel, and then each of these could further be pipelined to run on different processors. And this works because you're streaming in your frames, and then you're as you're processing the last bit of the current frame, you can start processing the first bit of the current frame. This is an example of finding concurrency in one of the algorithms. So these are some more generic examples. As you're going through time, each of these different processors, they're processing things in a different way. So one nice thing you can do with the Epiphany is OpenCL. You can essentially simulate SIMD on it by giving the same program to every single core. You can also do, with a bit of effort, you can do some more advanced things. You can do your typical divide and conquer, so stuff like quick sort you can do in parallel, and you can do that by forking and moving it onto different cores as you go down. You can do other server client stuff. So that's the first parallelism bit of the talk. And I'm going to talk to you about stuff that goes wrong with parallelism. So deadlock and race conditions. So first on to deadlock and the dining philosophers. So this is an example of how deadlock can occur. We've got our 5 philosophers sat around the table, and they're each about to eat some spaghetti, I think the tale goes, but they each need 2 forks because they can't pick it up with 1 fork. So they each, with their left hand, grab a fork. But now they can't grab another fork because everyone's got a fork and nobody wants to give it up. So we've reached deadlock again. No one's willing to give up, and no one can move forward as as a result. So, deadlock. You get deadlock because of the resources that you try to grab. And it comes from these 4 conditions. If, and I will go through each of them, but if you break any one of these, you break the deadlock and you fixed it. So, mutual exclusion, only one task can hold the resource. If you have mutual exclusion, then you're holding your fork and nobody else can grab it at the same time. And that leads into resource holding. You hold on to your resource rather than giving it up after a specific period of time. If we had a timeout on the fork, if they put it down after 10 seconds of not being able to get the next fork, they would break the deadlock. Preemption. If one of the philosophers could steal a fork from another philosopher, then you'd be able to break the deadlock. And then circular waiting. As you saw on the table, they're each waiting on the next person to give up their fork. So you can fix this. In this case, we're going to fix it with giving up your resource after timeout. So Plato here is going to give up his fork, and then Epicurus can do it, and then as we go along, they each get 2 forks at the same time, so they can each eat their spaghetti. And we've successfully broken the deadlock here. They've all managed to get 2 forks at the same time, so they've all managed to eat their dinner. And that's deadlock. I'll show you a few more examples of how that can happen later when we get towards the interconnect. Now on to race conditions. Race conditions occur because 2 things running in parallel without synchronization, and you don't know which one will come first. So it's a non-deterministic thing in programs from 2 parallel programs, each trying to beat each other to the end point. And a good example of this is 2 threads. Each is trying to print a message to the screen. So if we're wanting to get hello world, goodbye here, there's a 1 in 6 chance of doing it. And it's interesting to note that each of these threads will execute sequentially, so you'll always get hello before world, but you will get good and bye interleaved a bit in one of these ways. And we essentially cannot say which way it's going to happen until we execute it, and it might even be different every single time. And I've got a few more examples of this in conjunction with the interconnect and how we can solve them. So before I go into that, a quick look at the interconnect, the emesh. So you can see here there's 3 different interconnects, each colour, and each one is for a different purpose. One's for read, one's for write, and one that's not currently used much, the off-chip mesh. And it's interesting to note that you can write to the write mesh every cycle. So the processor, you can do a write to any location in memory in the address space, and it will jump out from the core onto the write mesh and then route to the destination node. And that can be done every single cycle. However, a read transaction takes a total of 8 cycles. And then once it's propagated to its destination, it has to respond. So writing is always better than reading for this particular architecture.
Is this specific to the Parallella?
This is specific to yes, the Epiphany architecture.
Yeah.
It's their mesh which does this. And this is also specific to Parallella, but it's a general example of dimensional routing, where you propagate east or west until you hit your destination node, and then you propagate north or south until you reach your column, then propagate north or south until you reach your row and you're at your target. So here we've got core 32, 32 trying to reach core 39, 39, and it'll go along until it reaches the column 39, then it'll go all the way down until it reaches the row 39. And then, because it's a read transaction, it does the reverse. So it's sent a source address with it, and then it can propagate back. So the eMesh has got some interesting determinism quirks. In particular, there's this point here. The point that if you write to a core, then attempt to read back that same value, you might not get the same value. Because the write mesh and the read mesh are different networks. The write mesh is a lot faster than the read mesh. Your write will sometimes get there first, your read will, takes a bit more time. Stuff happens in an indeterministic order. So this is the one key thing that you've got to be aware of when using the eMesh. So this is an example of stuff that works. So our objective is to print hello world in the right order. And we've got some sort of implicit synchronization here. So we're waiting to send to core 1, then we're waiting to receive from core 0, print hello world. Everything's worked. And now onto a slightly unsafe example, which is a good example of the race conditions that can occur. So because we're doing 2 writes at the same time, the order is specified as non-deterministic in the spec. So what can happen is, if we're lucky, this will get sent first, then this will get sent, and we've got our hello world. If we're unlucky, the second write will propagate first and get to its destination, triggering this implicit synchronization, and we get our wrong ordering. So this could be a problem. How do we make it safe? So we need to synchronize at some point. So we have exactly the same, except we've inserted an extra send and receive here. So these are, I've written it quite abstractly, but you can implement it this way on the actual Epiphany device, and you'll get, if you wait to receive here, you'll get an implicit synchronization. So this always has to happen first, because this sends this asynchronously, it then waits here. It then receives its message back from 1 saying, I've completed. And we always get this. So we've eliminated the 2 writes following each other, and we'll always get this ordering. So once we've made it safe, can we make it fast? So the write mesh is non-blocking. It's a lot faster than the read mesh, and this gives you the property of you want to write to external memory and never read from it, whereas you can read and write from local memory. You've got all of these buses here connecting your processor to the different memory banks, so you can read from them fast, but you can't read from the network fast. So here's a simple example, and it's interesting to note that this might actually fail due to the fact that you're reading and writing from an external core. We're running this on core 1, we're reading and writing from this external core 1, we've got this read and we've got this write, we've got another read and write, and it's not deterministic if those will actually end up in the correct order, which makes this likely to work, but possible that it won't. So what can we do to make this, oh, another point, this is slow, because we're reading from core 1. We've got to send a message to core 1 saying, can I have your value C? It will then return with value C, we'll then perform our multiplication, our addition, and then we'll send the result back to C. And this happens for every iteration of the loop, causing 10 reads, 10 writes. Whereas if we just copy just copy, there's a step missing here. We're supposed to copy it from C first, but the thing is the same. We hold it in a temporary on current core, and then we'll send it to C at the end. So there's no writes in this body of the loop. It can execute fast, it's running only locally, and then it can send the result. You get the same thing if you were just pushing results rather than having to do this summation. If you were just writing to an array on a remote core, you could just push it into the network and not worry about actually having to do this transformation. And now, this looks nice and simple. There's only a few modifications from the previous example, but it's a bit more tricky to optimize, as in each stage of this loop we're reading from a different memory location on this remote core and then performing our calculations. So I've come up with a few different ways of actually doing this. So, simplest way, just on core 0, execute it. We don't care about the reads. It will execute fairly slowly, but still. It will do a read for each item of this. It will do the summation. It will then send it back. We could also do the exact same thing on core 1, but then we've also got two reads. We've got read from AI and BI, so that will be even slower. And then there's various other ways of decomposing it. So you could copy the array from core 1 to core 0, do the calculations and send it back. This has the advantage of there's no reads at all across the network, so it should execute faster than either of these. You can also do the opposite. You can send A and B to core 1 and then just do the calculation. I haven't had a chance to run these yet, but I predict these would take a very similar amount of time due to the total number of traffic along the network is very similar. And then there's another way of decomposing it, of partially computing the results, sending it, and then doing the summation. And I think this one might be the best way of doing it, unless you have any extra ideas. So, while thinking of this, these are all fairly non-parallel, because you're sending something and then you're waiting for something else to happen and then you're getting the results back. Whereas if we could take the pipeline approach, we could construct something like this, where we process one item, send it on, have a synchronization so that we don't start executing on data we haven't received yet. And this again might be even faster due to the parallelism that we get. But a question to you, do you think it'll be faster? I haven't run it yet, so I don't know. So, overall, there's lots of different paradigms for parallelism. I've talked about many different ways you could hopefully extract some parallelism from your algorithms. Talked about deadlock, talked about race conditions, and the Epiphany's mesh throws up some unique challenges of determinism and how to structure your algorithms to make them perform fast. And if you want more information, there's those out there, and I'm happy to answer any questions.
I've got a question. So the thing you haven't mentioned is about how the processes get assigned to processes.
Yes.
And that's
Coming next.
Okay, right.
Coming next.
Is there a way of sending those calculations to the other processes and then signalling when those processes start as a form of synchronization?
So, yes, essentially. I think you can do it with interrupts, you can do it with sending an interrupt to the remote core and then waking it up at each point. So that's what I was kind of going for here. This would send an interrupt to this core, which would take it out of an idle loop, then it would continue processing.
On that slide, wouldn't it be handy if that sync operation also passed the data item that's just been computed?
Yeah, definitely would. And then you start getting into, rather than this shared memory paradigm, into message passing. And I think that's what would be a really good abstraction there on top of this. If you had a small, lightweight message passing library which could just be used to send data from one core to another core. And if I get a chance, maybe I'll write one.
It's called Occam.
If you want to put Occam on here, I'm sure lots of people will be interested.
We briefly lost Andrew, but I can't remember. I think, is someone working on getting Occam running on
I'm not sure, to be honest. There's
there
mention of it, but I'm not sure whether.
There are community groups trying to get every language under the sun working on this process. So I wouldn't be surprised if someone wants to get Occam on. I think when these become available, we'll start to see it's quite a good vehicle for student projects at university as well as hobbyists. So we'll see all sorts of things then. If someone wants to have a go at Occam,
Shall we?
be of interest.
You're explicitly reading and writing here, but presumably there are all sorts of DMAs that can
DMA.
be used.
The thing is, with the DMA, you'd have to completely finish processing on this array before you can start to send
Yeah.
it.
Well, if you could break it into
Yes,
sections,
I'm
then-
not sure. Yeah, you could definitely break into sections. It'd be interesting to find the threshold where that's faster and what size.
Would that make the reads quicker,
Um,
effectively?
I can't remember exactly, but I suspect you can do some sort of version of DMA. So it will, you say I want these 16 bytes and it will transfer them all. But that's an area of the spec I haven't delved into yet.
Can someone explain why the read bus is so slow in comparison to the write bus? It's the wrong way around.
So,
I don't know.
I think this is where you recognise we've got here all the software team and not the hardware team. So, well, it's Sunday, so it's a bit early to get Andreas out of bed in Boston. But the answer is, I mean, there is presumably some design rationale behind making write fast and read slow. But I haven't asked the team the questions. I don't know what. What it is.
Usually you're going to do far more reads than writes anyway.
Yeah.
It just seems all wrong. Intrinsically, reads are faster than writes.
Yes.
I think it may be to do with concurrency, in that you can be guaranteed that your write's going to work, but you can't be guaranteed that your read's going to work. So there's probably some overhead checking
Right.
Well, the
to
readers
prevent
are-
certain deadlocks, maybe.
As a guy who, before I joined InMOS, worked on memories, I was fed up with the delay that happened in the interface. People were asking always for faster and faster memories, and then putting loads of delay in the interface. With write, you've only got the delay in one direction. With read, you've got delay in both directions, so it's doubly worse. The access time in the actual memory itself is peanuts. It's the time in the bus.
it's completely through the mesh.
It takes the time, and if you've got to go all the length of the chip and all the height of the chip in order to get there, and all that to come back before you do the next instruction, that's going to take a long time. Fact of life. Global is phenomenally expensive, and
Yeah, well, hence the
local
emphasis
is
on
cheap
writing
as well,
only.
as Ian was saying.
And there are interesting features of the parallel architecture, which I think will become more exposed as we get the volume of people out there finding them. Certainly, one of the issues is there is a very small amount of memory. We're 30 years on from the transputer, and in fact we've only got 8 times the amount of memory on a core that the transputer had. And that's, yet we've got 64 registers. And it's got a very big register file, a 9-port register file, which is how it can do, it's a dual pipeline. It can do the DMA, the read, the write, and 2 instructions out of the register file all at the same time. They're interesting design decisions born out of, I think, prior experience with floating point units. It'll be interesting to see how they go. But the memory decision is proving to be an interesting challenge of partitioning problems down to where that size memory. you'll see that the future plan rapidly includes more memory. And in fact, one of the software, part of the software development going on is an overlay manager to allow to make for easier switching in and out of programs into that 32K.
Back to 1970s.
So, Parallella makes all sorts of interesting design decisions. One of the reasons, if you look at there are 64 cores on there, but it's still a tiny piece of silicon because Andreas will tell you that when he started this, he'd worked for years on floating point units, on chips that were supposed to be dedicated to floating point, and his floating point unit was just 1% of the chips. And a lot of the design philosophy behind here is what happens when you design a processor where most of the chip is the FPU. But as a consequence, there isn't much else on the chip. There are no caches or any of that sort of thing there. There is the FPU, there is the register file, there's a little bit of memory, and there's the router for doing the read, write and DMA.
What's the, if you've got a route that took you all the way to the edge and then back again, what's the response time as a function of that path length? Is it linear with that path length?
It's
Yeah.
one cycle per hop.
Right, okay.
So the adjacent processor is cheap, the one on the other side of the core. So you've got a whole localism thing, and that means your programs do need to know where they are on the chip when they're partitioning, or need to be written in a way that...
The compiler itself doesn't abstract any of that, does it?
No, the compiler does a very good job of parallelism within the core. So it unrolls the pipe, because it's a 5-stage pipeline, dual issue. It does a very, very good job of unrolling your program, vectorizing it, and keeping those both pipelines full. So, one of the problems GPUs have is they're typically pipelined, and the pipeline is always empty because they can't get stuff in there. We've measured more than 50%. Andreas, in some algorithms, got up to 70% pipeline occupancy using the compiler. And that's so you can use the individual cores very efficiently. The next challenge, which is beyond the compiler, is how do you then use all the different cores efficiently? That is a big challenge. Okay. So,
Sorry,
yeah, sorry.
you mentioned is it faster and things in the keynote was measuring. What tools are there for measuring in terms of?
Windows.
That's
it.
next.
Okay.
There's event timers and lots of stuff. So.
Yes, there's useful stuff.
One of the things actually James has done, which he did last summer, was actually also to measure the energy consumption. So I'm not sure where it is at the moment, but there is one very early Parallella prototype which has been hacked to pieces to insert what is essentially a resistor and voltmeter in the power line. It's a bit more sophisticated than that, in order to be able to sample the power consumption at very high frequency. And there is a research paper which is currently on archive and hopefully will appear in the Computer Journal before too long, actually looking at the power consumption on Parallella and how the compiler options affect that, which compiler optimizations are going to give you the lowest power consumption. Because, well, as I said right at the beginning, though Parallella goes fast, the thing that makes it really unique is the very low power consumption. So, we have hacked it around and done that too as well.
Just on that, is the Parallella board, does it have those current sensor resistors designed in it this time?
I think it does have
So
a
that we can-
current show. Yeah. So
We can monitor that.
I'm not sure how easy we can solve it, but they're definitely there.
Okay.
When we get one, we'll let you know. James has a new measurer, a new board for measuring that measures at 6 million samples a second, so we can measure very fine-grained power now. Not just this, on all sorts of